Welcome back to SSL TLS lecture series. This is episode 11 and I am Saravanan learning along with you. In today's episode, we are going to quickly learn how to provide authenticity and integrity for a message. We learned that in hashing function will typically provide integrity, right? But that alone is not enough. So we will see how to provide authenticity as well along with integrity. Then we will learn what is meant by non-repudiation and how it can be achieved using digital signature. We also learn the difference between the MAC and digital signature. Later we will see how to what is the typical technique used to design MAC. That is, there are basically two ways. You can build a MAC using a hash function, or you can also build a MAC using a block cipher. In this episode we will look at how to build a MAC using the hash function. The common technique which is used is called secret-prefix and secret-suffix. We will see what is the disadvantage in both the techniques. We will also go through the length extension attack, which is because of Merkle Damgård construction, which is typically used in hash function. Don't worry, I will explain all these details to you. We will also go through how to attack using different key sizes and message size. Finally, we will go through also the MAC collision attack and how to overcome all these attacks using a new construction called HMAC, which is nothing but a hashed MAC. We will also see a quick demo of HMAC SOR256 using Python as well as using command line. Okay, let's get started. In the past episode, we learned about hashing function, right? So what does the hashing function do? If you have a message M, if you take hash of the message, it will produce a hash value, right? We learned that the hash value basically provides integrity for the message. There is a problem with this hash value. Let's say you have a client and server, right? Typically, the client is sending the message as well as the corresponding hash value H. We have an attacker here. Let's say Oscar is our attacker, okay? He can tamper the message. He can take the message, tamper the message as M dash. He will also know somehow, let's say he knows the hashing algorithm. He can use the same hashing algorithm. He can recalculate the hash value and he can figure out the new hash value H dash, and he can also tamper this H dash. He can tamper both M as well as H, and he can send the modified M dash and H dash to the server. In this case, the server will use the same algorithm. He will calculate the hash. He will also get H dash which will match with this H dash. So it will ultimately pass at the server, right? That means he cannot use a regular hashing function because the attacker can modify both the message as well as the hash value. So that means the hashing function only provides integrity. It does not provide what is called authenticity. So what is authenticity? Let's say Alice is sending a message to Bob Mint. When Bob receives the message, he should be able to be 100% sure that it's really coming from Alice and not from some outsider like Oscar, okay? So that's what we mean by authenticity. That is the source confirmation. It is really coming from Alice. So a normal hashing function such as the MD5, the other hashing function that we saw, SOR1, SOR2, SOR3, all these guys will only provide integrity. They will not provide authenticity. So how to achieve authenticity in that case? Authenticity can be achieved using what is called a MAC, which is nothing but message authentication code. Just here I am using a simple notation authn, so to refer authentication, okay? So MAC means message authentication code. This fellow provides both authenticity as well as integrity. Authenticity as well as integrity. Whereas a typical hashing function provides only integrity, whereas a MAC provides both authenticity as well as integrity. So in order to calculate the MAC, let's say in a normal hashing algorithm, right, to calculate the hash value, you only need the message M, right? You only need message M, you can get the hash value. Whereas to calculate the MAC along with M, you also need a symmetric key K so that you can produce the corresponding hash value. So if Alice wants to send a message to Bob, both Alice as well as the Bob, they all know a symmetric key K. So using the symmetric key, Alice can calculate the H value. So she will send MAC as well as the H value. On the receiving side, Bob will use the same MAC algorithm. Whatever message he received, he will take it as an input. He knows the symmetric key K. So he calculates the value H dash. If H dash is equal to H, that means the authenticity is verified. the integrity is also verified. Both are verified. Why do I say authenticity is also verified is because the key K only Alice and Bob will know, right? So Bob is for sure, he knows that he is not the sender. That means the only other person who know the key is Alice. That means the message is really coming from Alice. So that's what we mean by authenticity. In this case, the outsider Oscar, he cannot perform the attack because in order to perform the attack, the Oscar need to know the key K, right? Here Oscar doesn't know the key K. That means he cannot perform the attack. He can modify the message, but he cannot modify the H value. If you want to modify the H value, that means if you want to regenerate the modified H value, he need the key K. So without the key K, he cannot regenerate the H value. So MAC is a better option than the hashing function. In fact, inside SSL TLS, we don't use the normal hashing function. We will only use the MAC, okay? So later we will see what exact MAC which is getting used in SSL TLS. There is one problem with MAC also. I told you MAC provide authenticity as well as the integrity, right? So let's say as usual we have Alice and Bob. Alice send a message, maybe the message is a contract, okay? She also sent the hashing value H. Later for some reason they both became enemy. Alice and Bob became enemy, so they got into fight. So they went to the judge. They went to the court and they went to the judge. Bob is telling the judge, hey guy, Alice sent me this message M and H. Here is the proof. I have the so-called MAC value for the message he sent. Can the judge accept this as a whatever proof that Alice really sent this message? The judge cannot, right? Because both Alice as well as Bob know the key. So Alice can tell the judge that the Bob fellow has used his key and create a fake message as well as the hash, right? Because both the parties know the key. That means if you go to the court, you cannot prove that using M and H that the message really coming from Alice. So this property is what we call as non-repudiation. Non-repudiation means after sending the message, you cannot deny that you didn't send the message. So using symmetric key, it is impossible to provide the property called non-repudiation. Non-repudiation means after Alice sent a message, she cannot deny that she didn't send the message. That's what we mean by non-repudiation. So MAC does not provide non-repudiation. That means using symmetric key cipher, because in symmetric key more than one person know the key. That means using symmetric key cipher, we can never ever produce non-repudiation. So how to get this non-repudiation? If you want non-repudiation, you can get using what is called a digital signature. Digital signature, usually we will use asymmetric cryptography. So let's see a very quick example how to provide this non-repudiation. So when we talk about the digital signature, right, there are so many algorithms for digital signature. The most commonly used algorithm is RSA, and we also have another algorithm called digital signature algorithm. It also has another name called digital signature standard. You also have one more algorithm which is popularly in use called elliptic curve digital signature algorithm. Okay. So in this, I will quickly go through the example using RSA. RSA being a public key cryptography, don't worry much about RSA. We have a separate episode for RSA. There we will detailedly discuss how RSA works. For the time being, assume that RSA is a public key cryptography. That means Alice will have two keys. Alice will have her public key. She will also have her private key. Let's say Alice wants to send a message to Bob, right? So she will take the message. This is her message. The message size can be anything, right? It can, let's say her message size is 1 gigabyte. That means he cannot totally encrypt this message for signature purpose because the size is so huge. You never know the size of the message. It can be 1 kilobyte, 1 megabyte, 1 gigabyte. So instead of directly signing the message, the common technique that is used is you first take the hash of the message. For this, you can use any hashing algorithm. For example, you can use MD5. Since MD5 is no longer safe, better don't use this. Let's say you use SHA-256, okay? So you get the hash value. Then this hash value, you encrypt using the Alice private key. There is a beauty with RSA. That is, not only RSA, in public key cryptography, there is a beauty. Usually you will have two keys, right? You will have public key and private key. If you have your data D, if you encrypt the data using public key, the only other key which can decrypt this is the corresponding private key. Similarly, if you have the data D, if you encrypt this data using the private key, the only other key which can open this, that is which can decrypt this, is the corresponding public key. So these two keys have special relationship like this. Okay, using the same key you cannot decrypt. Okay, in order to decrypt you need the other half of the key, the other key. If you encrypt using public, you need private. If you encrypt using private, you need public. Okay, in this particular situation for digital signature, we are going to make use of this property, that is you are encrypting the hash value using the alias private key. So after encrypting, whatever you are getting, this is what we mean by digital signature. Okay, this is what we mean by digital signature. So Alice will send this value to the Bob. So she send her message. The message doesn't has to be secret. Only she wants to make sure that nobody tampers this message. Okay, she want to provide authenticity, integrity, as well as non-repudiation. All the three property she want to provide. So along with this, she will send the digital signature of this particular message. On the receiving side, what Bob will do is, on the receiving side, he will receive the message and the corresponding digital signature. He will first take the digital signature. He will decrypt using Alice public key. The public key, the whole universe will know the public key, right? Public key is not a secret. The entire world will know the public key. So Bob also has access to Alice public key. So he decrypts the digital signature using Alice public key. After decryption, what he will get inside, you have nothing but the original SHA-256 value, right? Then Bob will take this message using the same SHA-256 algorithm. He will calculate the hash value, h dash. If both this and this are matching, that means the signature is verified. That means the authenticity is verified, the integrity is verified, non-repudiation is also verified, because in the whole universe, the only person who was having the private key is Alice. Nobody else have the Alice private key, right? That means we get all the three properties: authenticity, integrity, and non-repudiation. So in summary, a MAC algorithm will provide only authenticity and integrity, whereas a digital signature will provide you all the three. Okay. So since right now we are discussing about the MAC, don't worry about the digital signature here. So we will continue our focus on MAC algorithm. Okay. If you want to build a MAC algorithm, what is the common approach? What your logical sense tells? We have a message M, we have a key K. So if some way we can combine both the message and key, that will be much easier, right? So one possible way is you take the hash value, you take your message, you prefix your key K, and then you take the hash value. So this method is called secret-prefix method. Secret-prefix MAC. Okay, because you are prefixing the key before the MAC. Alternatively, what you can do is you can take the message, you can suffix your key, you can concatenate your key after the message, and you can take the hash value. This method is called secret-suffix MAC. Secret-suffix MAC. Okay. Unfortunately, both the secret-prefix as well as the secret-suffix are not cryptographically safe. There are certain kind of attack you can perform on both the method. So let's quickly see what attack you can perform on secret-prefix and secret-suffix, and why ordinary MAC you cannot use in SSL TLS. When we use the secret-prefix MAC, we can perform what is called a length extension attack. Of course, with all the MAC algorithm you cannot perform this attack. There are some MAC algorithm, it is designed using what is called a Merkle Damgård construction. Merkle is a cryptographer. Damgård, it's not a English language word. Merkle Damgård construction. So some of the hashing function internally it use what is called a Merkle Damgård construction. Almost all the hash function, most of the hash function designed from 1980s all the way to 2010, right? Almost all of them is based on this so-called Merkle Damgård construction. People usually denote this as MD construction. Okay, this MD, don't confuse this with the message digest. This MD represent Merkle Damgård construction. If you looking for example, right, the popular MD4 algorithm, MD5 algorithm, SHA-1 algorithm, SHA-2 algorithm, all the algorithms are basically using the so-called Merkle Damgård construction. So the length extension attack is possible if you are using this so-called Merkle Damgård construction in your hash function. So the way the Merkle Damgård construction works is something like this. Let's say you have your message m, right? It will usually divide the message m into blocks. For example, let's take the example of SHA-256. In SHA-256, the input block size is always 512 bits, whereas the output is 256 bits. Okay. So the message is divided into n number of blocks. So let's say m1, m2 up to mn. Okay. You are dividing your message into 512 bit blocks. Each block is 512 bit. If the last ending is not enough number of bits are there, typically you can add padding bits. Okay. So you add necessary padding bit and make sure it becomes the multiples of 512. We are discussing here SHA-256. So each of the message you can take as the input. So if you look at here, right? So I have m1 as input, m2 as input, mn as input. Merkle Damgård uses what is called a compress function. Don't worry about what the function does. Basically, it takes two input. It takes your message. It takes a initialization vector called h0. It's an initialization vector. This vector is equivalent to your hash value. Okay. So this is equivalent to 256 bits. So you initially provide a IV along with the message. This compression function completely compresses the whole thing and create an intermediate value called h1. This you pass to the next block. The next block will take m2 and h1 and create another intermediate value called h2. So the final value that you get is what is called a hash value. That is the output of SHA-256 hash function. Okay. So this is called Merkle Damgård construction, and because of the nature of how it works, length extension attack is possible. If you notice that, right, for every successive block, you don't have to worry about the previous block m1, h1. All you need is the h1. All you need here is h2, right? You don't have to worry about the previous m1, h1, all these things. So in this case, what will happen is, so the length extension attack, how it works is, let's say you have key k and message m1, right? You calculate the hash and produce the hash value. Later, you also attach another message m2. Then you calculate the hash value h2. Okay. Now, an attacker, what he can do is, typically what you will do, you will send the message m1, you send the h1 value to the Bob, right? Alice will send this detail to the Bob. So the Oscar sitting here, what he can do is, as long as he knows this value, all he needs is, he can take this value as well as he can insert his own message m2. Okay, his own Oscar message m2, and he can calculate the value h2. So he don't need to know the key, because if you look here, right, every successive block, you don't need the key right here. For successive block, all you need to know is, for example, here you only need to know h1. Here you only need to know h2. You don't have to really need to know the key, right? Only in the very first block, you are prefixing the key. So your key will be sitting somewhere here. For the successive block, you don't have to know the key. So because of the nature of this Merkle Damgård construction, with just the information of h1 and m2, only with these two info, you will be able to calculate the modified h2 value. So what you can do is, you can send now this new h2 value to Bob. So you send a appended message like this. Okay. You tamper the message, you also tamper you calculate the new h2 value, you send this new m1 concatenate m2 and the h2 value, it will pass at when Bob verifies this. Okay. So this is what we mean by length extension attack. All the hash functions that use Merkle Damgård construction is prone to this so-called length extension attack. That means I cannot use MD5, is prone to length extension attack. I cannot use SHA-1, prone to length extension attack. I cannot use SHA-2. All these are prone to the so-called length extension attack. Okay. So that means if I use these algorithm as secret prefix MAC, I cannot use. So how to overcome this, we will see a bit later. Okay. I cannot use this algorithm in secret prefix MAC mode. Interestingly, if you are using SHA-3 algorithm, right, when NIST announced the SHA-3 competition, one of the requirements to design the SHA-3 algorithm is it should not be prone to length extension attack, because they already know that SHA-1, SHA-2 is all prone to length extension attack. So when they announced the competition, the design requirement is SHA-3 should not be no one should be able to mount length extension attack on SHA-3. That's one of the requirement. Because of that, SHA-3 is safe. You cannot perform length extension attack on SHA-3. Another attack that you can perform on the secret prefix MAC is the different key length attack. Let's say we can take an example. Let's say you have a message M1, okay. I use a hexadecimal value. The value for this message is DEF00 and your key K1 is a hexadecimal value 123ABC, okay. Now let's calculate MAC for this value. So what will happen? Your MAC is nothing but K1 concatenate M1, that is nothing but MAC of, what is your K1? 123 ABC. What is your M1? DEF00, right? So let's say you produce a hash value H1, okay. Now let's take another message M2. This message is a different message. Let's say this message is BC DEF00, okay. And I have another key K2. My key is different now. My key is 123A, okay. So the message is different, my key is also different. So let's calculate the MAC for this. MAC is nothing but K2 concatenate M2, right? So which is nothing but MAC of, what is your K2? 123A. What is your M2? BCDEF00, right? So if you look at the value inside, right, both the value is actually same. Even though your key is different, message is different, the value inside the MAC algorithm is same. So obviously your H2 is nothing but same as your H1, right? Both will end up with the same hash value. So you will end up with a collision, some kind of collision, right? So that means this is what we mean by different key length attack. So you cannot use secret prefix MAC. It's prone to different key length attack. Of course, there are ways to overcome this. For example, if you are using a Blake 2 algorithm, right? Blake 2 algorithm, there is a way to overcome this, okay. In Blake 2 algorithm, or even if you use SHA-3 algorithm, they are not prone to this attack. If you use secret suffix MAC, right, secret suffix MAC is prone to what is called a collision attack. For example, let's say if you found a collision between two messages, right. So we already learned about the collision in the past episode. The collision is nothing but two messages will produce the same hash value H, right. So in this case, what will happen is your MAC of M1 and K and MAC of M2 and K will both end up with the same value H. So you will end up with a collision. That means the secret suffix, if your underlying hash algorithm is prone to collision, then you cannot use this. So how to overcome the secret prefix and secret MAC problem? So to solve this problem, a new algorithm was designed called HMAC algorithm. It's nothing but a hashed MAC. So it also uses the key K, okay. So this HMAC was introduced in a research paper by three cryptographers called Mihir Bellare, Rand Canetti and Hugo. I don't know how to pronounce this word. So if you regularly read cryptography paper, right, you can routinely find this guy, the Mihir Bellare. He's a very famous cryptographer, and they combinedly produced a paper sometime around in, I think, June 1996. So this paper is very famous. This paper is called HMAC. So they are the one who introduced the HMAC. So the Mihir Bellare, he is a very famous cryptographer. He is working as a professor at Department of Computer Science and Engineering in University of California at San Diego, okay. The other two guys, Rand and Hugo, they are the researchers at IBM TJ Watson Research Center in New York. You can find more information about the HMAC algorithm in the RFC 2104. Later this RFC was updated, so you should also refer the updated RFC, okay. The updated RFC is RFC 6151. So you have to read both this as well as this. So HMAC algorithm is extensively used in SSL TLS. In fact, whenever we say MAC, we always refer to HMAC in SSL TLS, okay. So NIST, the US NIST, they also have the special publication for this. It comes under the Federal Information Processing Standard 198.1. Let's see how the HMAC algorithm works, okay. For the HMAC algorithm, as usual, we need the message as well as the key. In addition, we need two fixed value called inner padding and outer padding. The iPad is not Apple iPad. It's called inner padding. The value is fixed at hexadecimal 36 and outer padding value is fixed at hexadecimal 5C. The algorithm is very simple. You take your key K, you XOR your key value with this IPAD value. Okay. Then you prepend the whole whatever output you got, you put it as a prefix in front of your message m. So the resulting value, whatever resulting value you get, you take the hash of this value. Okay, you take the hash of this value. For this hash, you can use any hashing function. For example, let's say we are going to use SHA-256. Okay, so for the hash, you can use any hashing function. In this example, I am going to use SHA-256. Then you take the same key k, you do a XOR with the OPAD value. You do the XOR with the OPAD value. Whatever value you get, you use it as a prefix to the already calculated output. Okay. Now you take a hash for the entire whatever info you have, you take the hash. This hash is also nothing but you can use any hashing algorithm. In this example, I am using SHA-256. Okay. So if you carefully look, your message is only hashed once. Okay. With the whatever this value. So this construction is called HMAC construction. So here you are using hash with the key using IPAD once and with the key with OPAD once. So you will overcome the normal deficiency of MAC algorithm using this special construction. Okay. So you cannot perform the regular secret prefix MAC attack, secret suffix MAC attack on HMAC. It's much safer from all those attacks. So nowadays in SSL TLS, whenever we say MAC, we only refer to HMAC. So this is what it is used. So if somebody told you you have to take a HMAC, you cannot blindly say HMAC. You should ask what hashing function should I use. So for example, you can have HMAC MD5 if the underlying hash that you are using is MD5. You can have HMAC SHA-256. You can have HMAC SHA-512. Okay. So HMAC alone, there is nothing called HMAC separately. It always comes with a corresponding hash function. Okay. So MD5 is different from HMAC MD5. SHA-256 is different from HMAC SHA-256. Okay. When we say HMAC, we are actually using this algorithm. Now you might have asked one question. Let's say my key is the 128-bit key. Okay. And my OPAD is only, my IPAD OPAD are only 1 byte, right? So there is no way I can do a XOR with a big number and small number, right? So to solve this problem, what you can do is, let's say your key is 128 bit. Let's say you are using a SHA-256 algorithm for your hashing. Okay. In SHA-256, I told you the input block size is 512 bits. Okay. The input block size is 512 bits. That means if you want to perform a XOR, right? So you take your key value, you expand the key value so that you can hit 512 bit. Okay, you expand the key value. Basically, you put your key, you add necessary zero so that you can make it as 512 bit. Similarly, you take your IPAD value. What is your IPAD value? IPAD value is 36, right? So you keep repeating the 36 enough number of times so that the length becomes 512, and then you can perform a XOR. Okay. The same logic you can use for your OPAD also. For OPAD, what is the value? 5C, right? That means you can repeat 5C up to you can make it 512 bit, and then you can perform your K XOR with OPAD. So basically you have to do necessary padding before you perform the XOR operation. So this is how the HMAC algorithm is working. I will quickly review the algorithm again. You have your key, you expand the key to necessary bit, you expand your IPAD to necessary bit, and then you perform your XOR. Whatever value you get, you prefix in front of your message. Then you take a hash. Okay, the hash can be anything like SHA-256 or whatever. Then you take the same key k, you perform, basically you have already expanded the key to necessary number of bits. You expanded your OPAD to necessary number of bits. You make a XOR. Whatever value you get, you prefix before your previous result. Then you again take the hash value. Okay. So this is what we mean by HMAC algorithm. So the HMAC suffix, whatever you see, it depends on what hash you use. Let's say if you use SHA-256, then it's called HMAC SHA-256. Okay. HMAC SHA-256 is much safer, and SSL TLS we are actually using HMAC SHA-256 in various places. Later we will see, okay, which are the places we are using this. In future episode we will see. Now let us see a quick demo of how to calculate the HMAC value. Okay, as usual I will first start with my Python 3. So I am invoking my Python interpreter. All the hashing algorithm is typically inside the module called hashlib. So I am importing the necessary library, and HMAC is under the module called HMAC. So I am importing the HMAC module as well. Okay. Then I am using a variable h. Basically I want to create a new HMAC object. So I say HMAC.new. I have to specify my password. Your password is nothing but your key. Okay. So here I am specifying my key as my password. I am using a byte string, otherwise Python will by default it will assume as a Unicode string and it will change the result. Okay, make sure you provide it as a byte string, that is the octet string. Okay, then I have to specify what digest mode. I told you, right, there is nothing called HMAC. HMAC always comes with a hashing function. You have to specify what hashing function you want to use inside the HMAC algorithm. For that I am using a option called digest mode. Inside I will say I want to use my SHA-256 algorithm. Okay, so it created a HMAC object and it's stored in the variable h. Then I need to tell what message I want to calculate HMAC. Okay, I'm going to say hello. Hello is my message for which I want to calculate the HMAC value. So you can use the update command so that it can calculate the HMAC value. The update command basically calculate the HMAC value for whatever message you are giving inside. Here my message is nothing but hello. Now I want to see the output in hexadecimal. For that I can use the hex digest command. So this is the HMAC value. So if you want to check the length of this, because I have used SHA-256, the length is going to be 256 bits. So let's do a quick check of this length. I am copy pasting this. Because it's in hexadecimal, I have to multiply by 4. So I got 256, right? So the output is a 256 bit value because the hashing algorithm I used inside HMAC is SHA-256. So the next demo we will see using the command line option. So I am going to use echo -n as usual. My message is hello. I am going to use the command line command HMAC 256. If you are using Unix or Linux, you can use the HMAC command line. If it is not there, you can install. So this command needs a password. So as usual, I give my password. So look at the output value. So it's same as what I calculated from Python, right? This is from Python and this is from command line. So let's see one more example. Now I'm going to use OpenSSL. Okay. So I will use OpenSSL. I'm going to use the digest module for this. So I have to tell what SHA algorithm I want to use. So I will say I'm going to use SHA-256 algorithm. I want to calculate HMAC value. Okay. The password I am going to use is as usual my password. This is the one I am going to use. So my input is nothing but as usual echo -n hello. The word hello is my input. So let's see what OpenSSL calculates. So I got exactly the same value with OpenSSL as well. Okay. I think with that we can stop today's episode. So in summary, let's quickly go through what we learned today. So at the beginning of this episode, I told you the normal hashing function will only provide integrity. That means the outsider can modify both the message and he can recalculate the hash value. In that case, it will pass at the receiving end, right? So integrity alone is not enough. We also need what is called authenticity. So a MAC algorithm, a message authentication code algorithm, will typically provide this authenticity as well as integrity. MAC uses a key K along with the message M, and because this key K is a symmetric cipher, it is not possible to achieve non-repudiation with a MAC algorithm. A non-repudiation means after sending the message, the allies cannot deny that she didn't send the message. That's what we mean by non-repudiation. Okay. So using symmetric key cryptography, it is impossible to get non-repudiation. For that, we need to use public key cryptography. In particular, we can use digital signature to gain all the three, that is authenticity, integrity, non-repudiation. All the three can be achieved using digital signature. We saw a quick example using the RSA algorithm, right? Then we also learned the difference between MAC and DS. Basically, MAC provides authenticity, integrity, whereas digital signature provides all the three. Okay. Since this episode is about MAC algorithm, we only focused on MAC. I told you MAC can be built either using a hashing function or you can also use a block cipher to design a MAC algorithm. In this particular episode, we only saw how to build a MAC using the hash function. We saw that there are two logical possibilities. Either you can use secret-prefix or secret-suffix, but both of the method has lot of possible attack. For example, if you are using the so-called Merkle Damgård construction, the underlying hashing function is prone to length extension attack or different key size attack or collision attack, right? We saw all the various different attacks that you can perform on Mac. So to solve all these problems, in June 96, some of the three famous cryptographers, Mihir Bellary and two other cryptographers, they invented something called HMAC algorithm. So in SSL TLS, almost everywhere whenever I say MAC, actually it's using HMAC algorithm. There is nothing called HMAC alone. There is no standalone HMAC. It always comes with a hash function. So you must ask whenever somebody say take a HMAC value, you should ask using what hash function. Okay. So we saw a quick demo of how to calculate SHA-256 using Python or using your command line or using OpenDigest. Okay. So with this I will stop here. I will see you again in the next episode. Thanks for joining today.